All right. It is 11 o'clock Pacific, which means it is 1 o'clock Central, and it is whatever time it is in your time zone. So we're going to get started here. Hello, everybody, and welcome to Quantum Analytics next webinar. Today, we're going to be tackling the science of polymer analysis from A to Z using the power of infrared and Raman spectroscopy. And in my alphabet, T is for Dr. Tom Tagg, who will be joining us today. Dr. Tagg is Applications Manager for Bruker Optics, and he'll be demonstrating the effectiveness of these instruments when it comes to quality control, identifying product defects or failures, reverse engineering work for product development. Dr. Tagg is a member of the Visiting Advisory Committee of the Metropolitan Museum of Art in New York and on the Strategic Advisory Board of Applied Sciences. He received his PhD from the University of Utah in physical chemistry and a Bachelor of Science in Chemistry from the University of Texas at San Antonio. He is a member of the American Chemical Society for Applied Spectroscopy, American Physical Society, and the Optical Society of America. I am Lauren Armstrong, Marketing Director for Quantum Analytics, and I'll be moderating today's event. Want to share a really quick note about quantum analytics before we get started. We are a value-added distributor of analytical instrumentation. We are your one-stop shop for the busy lab manager, offering everything from rentals, financing, and leasing on new or refurbished instruments, or consulting services for entirely new lab startups. We are a proud distribution partner for Bruker Optics, which means that our US-based clients can purchase the Bruker products you're learning about today directly from Quantum Analytics. As a registered guest, you're going to receive a link to this recorded webinar in your email when it becomes available. We've reserved about an hour for this event, which includes Q&A. So type your questions at any time in the text box in the question module that you see on the right side of your screen. We're going to keep a roster of the questions and pose them to Tom at the end of the webinar. Also, to keep things a little engaging, we're going to be asking a few polling questions throughout the webinar. When the poll question pops up, simply choose the best answer, and we're going to review the results with the group. All right, this ends my intro. So without further delay, Dr. Tom Tagg, take it away.
Thank you, Lauren. I'm excited to meet with everyone today to talk about polymer science. We'll cover A to Z, which means essentially the full spectrum of examples. And I have a couple of examples which I think you'll be very excited about as well, especially a good reverse engineering example. So with that, I wanted to kind of start from the beginning, just so that we understand what we're going to be able to do in doing an analysis. So when you have many tools at your disposal, as Lauren alluded to, when you're setting up an analytical lab, there are many different tools that you can use. If you want to do elemental analysis, you might want X-ray fluorescence. If you're looking at doing analysis of unknowns, I would argue probably infrared and spectroscopy is probably your first and best tool for looking at organics in particular. And amongst those many tools that are available, infrared spectroscopy gives you the advantage that it's non-invasive and very highly specific. And the way infrared spectroscopy works, just very briefly, is you're going to take a broadband infrared source, an infrared light bulb essentially, and you'll look at the emission as it interacts with the sample. If it bounces off, we'll collect the reflectance information. If it passes through, we'll look at the light that is missing due to absorption from the sample, and then we'll do the detection. So in this case, this is a very simple representation, but the instruments are fairly straightforward. We do use a Fourier transform infrared spectrometer rather than a dispersive-based spectrometer, and that has to do with the detectors. The detectors in this regime tend to have fixed noise floors, which means that you're better off collecting all the light at once rather than doing them one wavelength at a time. So just a small note. We're also going to go through a couple of examples with Raman. And so what is Raman spectroscopy? And just like in our previous example, we actually looked at sending a broadband light packet to your sample. Now you're going to actually send just monochromatic or single wavelength, very bright light to your source, to your sample. And historically, that's been a laser. So we'll use a laser. We'll use one of many different wavelengths available on our systems typically, and we'll look at the inelastic scattering that we'll do the detection with. We're actually not interested in the light that passes through, and as it turns out, that is the majority of the light that doesn't interact with the sample. We'll obviously ignore that. We're going to sit on the backside here and look to collect the data that's inelastically scattered from your sample. So some of the advantages of infrared and Raman spectroscopy. So for doing materials identification, it's just the absolute best tool, non-destructive and very, very specific. You'll look at functional groups. So each functional group has its own characteristic absorption position in the middle infrared region of the electromagnetic spectrum. And for Raman, even though we're looking at the Raman shift, that Raman shift takes place in the same region of the spectrum. So whether we're talking about IR or Raman, we're looking at those first vibrations, the ground state to the first excited vibrational state. And in those areas, each functional group pretty much has its own fingerprint signature. And you get the high degree of specificity because each functional group can be perturbed. Its absorption or scattering is perturbed a little bit by nearest neighbor, next nearest neighbors to give you that specificity. We're also going to look at reaction kinetics, so you can actually collect the data in time and look at the evolution of the process of interest. You can also look at homogeneity. So if you do infrared or Raman microscopy, you can actually collect chemical images of your sample and be able to look to see what you have there. And we have some beautiful examples we'll go through together there. One of the advantages of infrared and Raman spectroscopy as well is that when you look at the wavelength axis, it's very, very stable and very well defined. That means if there's a small change in a band due to a change in polymorphism or crystallinity, you'll be able to detect that very well. So crystallinity and polymorphic differences are very easily and reliably accomplished using vibrational spectroscopy. You can also do purity studies. So if you're looking at contaminants, one of the best ways to look at for contaminants is actually just to collect data from the whole area and then look for minority components. You can do that typically with a cluster analysis or something else. So again, they're really powerful tools for almost any materials, anything that has a covalent bond. And the areas where they're very applicable are in research, in development, quality control, and just doing fundamental science. As in talking with my children, you know, they say, "What do I do?" Well, I do science. So, and then we'll get into more detail. But when in today's world, there's so many different areas of science. I think that's maybe the best slide in describing that. So let's go to the first example. So in this case, we're going to use a simple ATR accessory as shown on the right. Non-destructive, doesn't require sample preparation, and the measurement can be accomplished in just a couple seconds. So what we would do is just put the sample of interest right on the sample plate. We'll collect the background without the sample there, and then we'll collect the sample, and they're usually ratioed to strip off the instrument response. Now this is just a really wonderful slide in showing many different O-rings. So O-rings are problematic in almost everything that gets done these days. And you can see many different examples. Sometimes they have a higher indices of refraction. We actually include the rubbers library free with our system. And you can see the benefit. Every single different rubber is very nicely characterized. Even the Viton black and brown are, you can see from this band at around 1180, that shoulder, they're still well differentiated. You can also see that the bands are sharp so that you can, you would be able to see small differences very reliably. So let's go through kind of a real life example. So this is a quality control issue. So we have a Viton black and we have what is supposed to be an EPR ethylene ethylene propylene example. When you collect the data, they certainly look very similar. And so, what's up with that? So we have the known spectrum, and then when we search the library for the EPR, it looks very different than the measured EPR spectrum. So what happened there? Well, what we can do is actually do the search, and as it turns out, we have the base spectrum that shows the VA151-75 O-ring, but then and you have the compliance there, but then the other spectrum could be searched and you get the answer very nicely there. And as you see here, we were able to identify the contaminant very nicely. Another really good example is looking at curing reactions. So if you have your sample, you just put it onto the diamond crystal, and then you allow the UV light to impinge on it. The diamond crystal is very robust, and so you're not going to damage the crystal by doing these types of experiments. And you can see from the graph on the lower right that over time, even a fraction of a second, you can see the reaction dynamics proceed very nicely. And so you'd say, well, okay, that's great for a one-time experiment. Do I have to throw the accessory out? No, once the epoxy cures and becomes very hard, it's actually very easy to remove. I usually will take a flathead screwdriver and a little ball peen hammer and knock the sample off the ATR accessory. So it's very easy to do. You can certainly then clean with whatever solvent you need. But again, the diamond ATR crystal, you have a single element diamond crystal brazed in a tungsten plate, so it's very, very robust. So in this case, we have the before curing and the after curing, and so we're going to do a quick collection where we're collecting about 20 spectra per second. And when we look at the dynamics here, we can see the acrylic polymer with the curing takes place predominantly in the first several seconds and then tails off by the 1 minute margin. When we look at how much additive we need, we can see that if we actually have 0.5%, the reaction does not proceed. But you can see, well, if I use 2.5% versus 4%, I can actually spend less money on the initiator and be able to do a really fine job. So again, understanding the reaction dynamics and then optimizing the components can save you real money. You know, obviously for a large production process, the difference between 2.5% and 4% can be substantial. So let's take another small detour and look at Raman and IR microscopy. So we talked about doing kind of static measurements. Now we're going to actually place the sample on a unit where the sample stage can be moved around. So in the FTIR's case, it may be attached to a system, an infrared spectrometer, to do macro measurements, as you can see the ATR accessory in the sample compartment, or on the stage. We also, as you saw previously, sell the standalone small alpha system. And the alpha and this is the Invenio system I'm showing actually have identical performance. It's only a question of whether you need different capabilities outside of the mid-infrared or some specialized experiment. Otherwise, the alpha will actually be at least as good as the Invenio for performance. And then for the Raman, we have the Raman microscope here. We also have a handheld Raman that is available and performs very well and analogously as the alpha does to the Invenio. So again, we want to take all of the capabilities of the single point analysis and apply them to the microanalysis. But now we want to have a spatially resolved sample where we can do a very nice job of resolving down to a few to several microns. And again, with ATR or direct reflectance and with Raman, we actually have very little sample prep that's needed. And now we can collect images to collect the distribution, the distribution of the different components. So you can analyze small samples or very large objects that can be put on the stage here. And again, we offer accessories that actually can allow the beam to be turned to the front or to the side for analyzing very large objects. So, and again, imaging, what that means is that now instead of collecting single point like we're doing with the ATR or with the traditional Raman, we're going to allow you to actually collect an image by mapping rapidly or doing a full field image where we collect like you would with your smartphone. In this case, I have a contaminant image that I'm looking at first, and then I have a colon section that I was able to image in one snapshot. Whenever you click on the live image there, you actually would see the full spectrum and can right-click to search it directly. So let's go to a good polymer example. So now we want to analyze the component of this composite material. You can see it's very difficult to see. If you look carefully, maybe you can see that there are a couple of different layers there. But actually, when you actually do the analysis, we can actually see with the micro FTIR that we have PTFE here. We have so we have the PTFE in green, the aramid in red, and the POM in the blue. So this is really wonderful in being able to look at the distribution. We can look at the particle sizes, and indeed I'll talk about this in more detail in a few minutes. You can actually count and size the particles as well as identify them and classify them. So if you try to do this by Raman, the Raman might work, but sometimes you can have fluorescence, but by the IR you don't have that. If you're looking at inorganic compounds, organometallics, they're usually the Raman is most necessary. So if you're looking for pigments and other things, the Raman will be much better. So organometallics in particular. And I mentioned that we have the standalone imaging microscope. This is collected from the Lumos 2 system. And again, if you don't look to do analyses in a macro chamber or have specialized experiments, you would have the Lumos imaging microscope that stands alone and the Alpha that stands alone. You don't necessarily need to connect them, and I might argue they're optimal, separate. You can put them together if you want to, though. So we're going to do our first polling question, and I'll turn it over to you for that, Lauren.
Fantastic. So let's everyone get ready to answer this first poll question. Is depth profiling important in your research? So select the best answer. Yes, very important, somewhat important, and not applicable. So everyone answer the question. Wow, a lot of answers came in really quickly. So I think we're actually close to being able to close this out. All right, here we go. Tom, I'm going to close this and share the results. It looks like 52% said somewhat important, 26% said not applicable, and 22% said yes, very important.
Well, thank you for that, Lauren. I think that that's a really profound result. About 3/4 of everyone attending are interested in depth profiling. So I'll spend a little more time than I normally do on that particular part of the presentation. So very good feedback. Okay, so the next thing I wanted to talk about are microplastics. So microplastics are in our environment. I would argue that global climate change is a big threat to mankind's future. But I would argue that probably microplastics are at least as big a concern, because global climate change has been shown to be reversible when you study the data. But microplastics in the environment is not reversible. So when you look at microplastics, what are we talking about? Anything larger than about 5 microns, to on down, we might consider microplastics all the way down to 100 nanometers. And anything down in that regime, they're really called nanoplastics rather than microplastics. As it turns out, those below about 800 nanometers are actually very dangerous to man for direct consumption. They get metabolized through the stomach efficiently and get into the bloodstream and hence into the brain. So the first publications on the risk of microplastics have been out for about 50 years, and there's just been an exponential increase in manuscripts that have been published on this topic. So you can look at garbage found on the beaches. Man has always left his trash around as long as man's been around. Complete decomposition can take many, many years. That's not really the worst part of this. The worst part of this is that if you take say a particle that's like 5 millimeters in diameter, and then when you look at it as it decomposes, it turns into thousands and tens of thousands of these very small particles that can get into the bloodstream. And certainly we see this getting with if you go catch fish in the ocean and then just go ahead and do the dissection and determine the microplastics content in the brain and in the muscle tissue, you'll see it, and it's virtually any fish caught in any body of water. So this is a really high risk area for man. So How did microplastics get in the environment? Again, societal use of plastics, domestic, industrial, and agricultural, as shown on the left, and actually they accumulate in the soils. And I actually live about kind of out in the middle of nowhere. I have a 350-foot deep well, and I can actually filter the water from my well and pick up microplastics. And I do not live anywhere near a main source of what you would consider microplastics pollution. So it really gets into the water effectively. There was a study that was conducted about 4 years ago where the researcher, she started at New York City, went up the Hudson River all the way to the tributaries, and found that the concentration of microplastics in the water was essentially unchanged all the way from New York all the way up to tributaries in very sparsely populated areas. So the microplastics are kind of getting everywhere. They're in the atmosphere as well. And so we need to characterize the presence of microplastics as carefully as possible in the environment. So we have two ways to do this, and I alluded to this previously. So we consider these unified approach methods both viable. So if you're going to filter the water, and we use an additive filter, we provide a kit with the system to do this. If you have just several to maybe a few hundred particles, you can actually hunt and peck them. So the software will go and find all the particles on its own. You don't need to do that. You don't need to mark them or anything else. And then it will collect the data and then show the results as a grouping of the size, the count, and the identification of each of the microplastics. If you have many particles, more than 100 or 200, then we'll actually image the whole filter rather than identifying individual particles, which should start taking a ridiculously large amount of time. In this case, we'll image everything, and then we'll use special software that we've partnered with Purency, a company that has specialized in this area for developing fast algorithms. And then you get the same information. You get the particle list, identification, and the size distribution. So the first step in the targeted approach, as I call it, is that the software will convert your visual image to a black and white image, and then it'll mark all the fibers and particles very smartly, and you can set the minimum object size you're interested in and the spatial resolution. Very easy to set in the software, shown on the lower left, actually in the software dialog. And so now, once you've done that, you can actually look at the targeting, sizing, identification, and counting. And as it turns out, it doesn't matter whether you want to do the IR or the Raman analysis, the software we have works the same way for all of our microscopes. And so again, you have the visual image and the correlated dark field image, and then the count. You can actually show each of the components. So say you wanted to show the calcium carbonate, you can show the calcium carbonate image as I showed on the previous slide. They're color coded. And then if you actually want to look at the additives, now we collect 15 million spectra in about, it takes about 30 minutes to collect all 15 million spectra. Again, there's no other system on the market that can touch that for acquiring so many spectra so quickly. And then when you do the analysis, just a couple clicks in the software, it takes 15 minutes of computing time to do the analysis on 15 million spectra. And you can see the data quality is really outstanding. And then you get the results that you want. So with having covered microplastics, let's go back to Lauren for our second polling question.
Awesome. Next question up is, what method do you use more? Select the best answer. Is it microscopy, imaging, or maybe something different, other? If it's other, feel free to include that in the chat, just so we can start seeing what other methods people use. But select the best answer, what most applies to you. And once again, lots of answers coming in. Fantastic. All right, I think I'm going to close up the poll now and share the results. Wow, that is overwhelming. 68% microscopy, 24% said other, and 8% said imaging. So 68% microscopy. Tom, interesting results.
Yeah, this is great. So we've got the right audience here, Lauren.
Woohoo!
Great. So let's go to our next slide. And this one is actually really interesting because this is important for polymorphic analysis and for polymers life testing. So, so if you want to look at the temperature-induced changes that might take place in a polymer, you can use one of a few different cells that we have available. This happens to be a Lincoln cell, and we'll actually place the sample inside the cell, and you can control the temperature and the humidity depending on which version of the cell you get, and be able to control it. So in this example, I'm just using a white powder, and we're going to look at a time resolve study. We're going to look at this band that's at around 680, and again, we're doing this by Raman for this example. So we're doing Raman microscopy evolution studies, and we can see that after about 150 minutes or 2.5 hours, and we go up in temperature, we can actually start to see the changes, and actually we see the degradation of the polymorph A and the change in polymorph B. So very, very cool. And again, you can actually click on at any point in the data curve shown here to pull up the actual spectra. The next one I wanted to show you, which is very interesting, this is an inhomogeneous distribution, a luminous stone. So it's an organic composite, and it's resin with filler and is UV fluorescent. So what it has some odd glow to it that the maker of this product was very concerned about. So was there pigment damage, or you know, what was the issue here? In many quality control examples like this, you really can't destructively analyze the sample. So we'll apply the spectroscopy looking at this small particle non-destructively. So the first thing we'll do is we'll image, and so you can see what it's like to collect the image live, and then you have the resin, you have the filler, and then you have the UV pigment that's there. So very nice to be able to get the corresponding image from each of the components in this stone. And then you can do what we call the red, blue, green rendering of the image, also known as the RGB. So you can see the chemical identity and the hot spots where there are problems from the UV pigment. So if we take a packaging example here, we have a multi-layer laminate for packaging, and we're going to take 5 microns per scan in the X direction, and they want to look at the proof of an ethylene vinyl acetate presence and identify the presence. Requires some confirmation. So when we look at this, we're going to scan across the packaging on its side essentially, and you can see the PET layer, the PA layer, and again the PE layer on the other side, and then the ester layer, and you can get the 2 micron, the EVOH layer. Very nice. So again, high quality data analysis very quickly and very easily by by doing this type of analysis non-destructively. So again, high resolution micro ATR imaging really works for even the thinnest laminates. So let's look at a large component. I mentioned that large objects can be placed under the microscope. So this is a large piece. We're looking at the electric motor housing. Again, you can see we're dealing with another polymeric product. It's 6.5 centimeters in height. So how do we get in there? And if you look carefully at the image in the center, you can see the ATR crystal is on the end of a stick that's on a piezo drive, and allows you to get into tight areas very nicely. So you can analyze large objects with very high resolution, but also with them what I would consider high dexterity of analysis and being able to get in there. So in this case, you didn't have to do any disassembly or destruction of the part to do the analysis. And there's the spectrum. Again, the micro ATR works. The crystal face is so small that your analysis area is such that you can just get into tight areas. You get a beautiful result in a single scan that shows the polyamide result. So let's look at an LCD display, and we're going to incorporate this into a larger study in a minute, and so you'll see it. So in the LCD now, which is important for in this case for the automotive industry, this was a sub-out part from one of the large automobile companies, and so they have these crystal dendrites, and so these are the fluorescing areas that I mentioned before in these types of displays. So you want to perform the measurement, and when we do that, we actually can see the matrix, and then we can see where the crystal is. And as we look at that, now to go a little further from what we did before, we want to do the identification. So you identify the matrix first, and then you can see that's dimethylmethicone, and so it has a trade name also polydimethylsiloxane. And so then you can subtract that off and then get the spectrum that you want. And then so now you have the matrix and the removed spectrum. I will point out that once you do this, you'll realize that the wavelength precision of the instrument needs to be really good so that you don't have any derivatization of the bands over time. So that seems like a small thing, but doing subtractions, collecting a spectrum today versus tomorrow or next year, the wavelength should be very much set without moving around. And the Bruker systems are the best in the market by quite a bit in providing that capability. Now, okay, depth profiling was really important to a lot of you. 3/4 of you said that it was either slightly or very much of interest to you. So this is one of my favorite samples that we worked on, and my colleague Pong and I published this as a communication a couple of years ago. So now we have 7 layers that we have in this multi-layer polymer film, but it has a metallic backing. So what's nice about this is now we're going to march through by bringing the sample up and doing Raman. And we're actually not going to microtome it. We're not going to mount it up or anything else. We're going to leave it flat on the microscope and just bring it up through the field of focus and then continue to bring it up. And lo and behold, what we see is that we can see the principal layers shown here on the left, and then we reflect off the backing and then can see the other layers, these same layers come back into focus having bounced off. So you can see the precision of the system where you can actually see beautifully not only the principal analysis, but also the back reflection off the back film and resolve each of these pretty much down to the baseline, even though they're only several microns thick. And then when we look at the spectral quality, again, you can see the polyester, the polyethylene, the nylon polyethylene, and just wonderful example of being able to go through onto the metal layer and then back through again. And maybe the best example I've ever seen for confocal is actually the syringe. So in the visible image, you'd say, well, the image quality is not very good. But what we're doing with the microscope is we're actually looking through packaging of the syringe, and we're looking through the syringe wall, and we also have some fluid in the syringe, and this particle doesn't belong there. So the image quality, I feel, is just outstanding, looking at a suspended particle in a solution in a syringe through the packaging. And we can see the syringe material, the gel content that's in the syringe, and then we can see the polypropylene contaminant that's in there very nicely. So this is, in this case, you actually don't need a high resolution objective to do this, where you're trying to get micron resolution like I showed in the previous example. Now you'll just use a 10x objective, and it works great. So many forensics institutes around the country use our Centera Raman microscope for real world examples. And one of the reasons it's found favoritism there, I would feel, is that because it's so good at confocal, even what I call macro confocal, where they can take a bag of drugs that may have been found in a suspect's toilet, and then just throw it into a chain of custody bag, and then using a 10x objective, they can look through both baggies and be able to analyze the active ingredients or the drugs very quickly and easily. So you can focus on the surface, or you can focus on what's underneath the surface and just do a fabulous job. And Bruker has a patent on how we do the confocal work, and I feel we're the best in the industry, whether doing macro depth profiling or micro depth profiling. So after that exciting example, let's go to our third polling and last polling question.
Awesome. Here we go. So last polling question is, how often do you need to analyze small particles? I'm going to launch the poll right here. How often do you need to analyze small particles? Got to choose the best answer, which most applies to you. Is that most of the time, sometimes, or perhaps it's rarely or never? Choose the answer that best matches what you experience in your job. And uh, once again, you guys are really quick on the polls, which makes my life easier. So I'm gonna just close this up in just a second. A few last entries coming in. All right, here we go. Looks like 64% sometimes, most of the time 20%, and then rarely or never 16%. Tom, there we go.
That sounds great, Lauren. So let's move on, and I want to look at a whole package analysis. I've given several what I feel are really good partial examples, but let's do a real world one. So we're going to look at a phone, and we want to analyze all components of it. So again, this is a tailor-made solution to analyze the entire product. So the first thing we're going to do, we're going to look at the electronics. So for the camera, characterization of the optical components and sensor technology. So again, we're going to use our IR and Raman microscope tools that are at our disposal. So we're going to look at the multi-layered system of the optics, the display technology, and we want to do this non-invasively and with high resolution. So again, this phone uses this LCD example that we looked at previously. So this is the first part of it. The next part, we're going to look at the battery. So batteries can be analyzed very nicely. We want to look at the battery technology here. So now with these same tools, we're going to look at the anodes, the cathodes, the electrolytes, and the charge and storage reactions. So we can actually do the reaction dynamics as we talked about. And we can also do these analyses in a glove box or look at side products. So again, as I talked about before, now you can look at the lithium carbide battery and look at as it's deposited on the copper and do the analysis in a glove box in an inert atmosphere, and showing that example from before now inside the bigger picture of looking at all the components of this phone. So how about the casings and such? So now for the quality control and defect analysis for the polymer parts, we want to see what that stuff that didn't belong there in the lower left-hand corner. And again, we can look at additives, fillers, plasticizers, multi-layer laminates, coating, thickness, material, research, and such. And again, these are very fast, non-invasive analysis. And we showed that example before where we can actually analyze single particles with the ATR unit in a macro manner, as shown in the lower right-hand corner, or you can do the multi-layer analysis as we showed previously. Excuse me. I hope that wasn't too loud for you. And then one of the nice examples here is actually looking at root or cause failure analysis. And so looking at cleanliness. So, and again, we're able to look at things below 5 microns and down below 0.5 microns with Raman. And again, we're looking at organic with IR and inorganic for Raman typically, and we can do an automated particle analysis. So in this case, we've got the contaminant, crystalline contaminant across the soldering joints. There's the contaminant, and then we could do the analysis quickly and easily. And the last example is looking at surface refinements or issues that might be right on the polymer surface. So looking at the coating thickness, uniformity, quality control, process evaluation. So again, non-destructive and looking at both organic and inorganic coatings. So in this case, we're looking at the coating thickness. This can be determined directly in the software, and you can see the thickness on the right here on the scale. So very nice in being able to see not only what's there, you can click at any point on the image to see the spectrum, but you can also calculate the images directly. Calculate the thickness correctly. And we have many lubricant manufacturers that use this system routinely for doing those types of measurements. And with that, in summarizing, we have infrared and Raman microscopy. They deliver complementary molecular information. Just note that the infrared gives you the antisymmetric modes of vibration information predominantly, works great for organics. And the Raman gives you the symmetric modes of vibration, so, and also gives you polymorphic information down below 400 wave numbers, and works well for what we call phonon modes down there, which is great for differentiating polymorphs and looking at organometallics, so pigments in particular. So Raman also gets you down to less than 1 micron easily, and FTIR usually a few microns. And the Alpha 2 is the tool really of choice for scientists in this field for doing the analysis of larger particles and such. And if you need to go to other spectral ranges or time resolved measurements or other of those specialized applications, you can go to the Invenio. And then the Lumos 2 and the Centera 2 are our IR and Raman microscope platforms that are well proven in the industry. And with that, I'd like to thank you for your attention and move to the Q&A session.
Fantastic. Well, Tom, another great webinar. Let's dive into a couple questions here. And just a reminder to everyone, if you do have a question for Dr. Tom Tagg, you can type it into the question module that you see on the GoToWebinar control panel, and I will add it to the queue here. All right, so Tom, first question. The in-syringe imaging is very impressive. Can you speak towards how much penetration is possible?
So the depth of penetration actually is a function of the numerical aperture of the objective that you use. So if you want to do these microfine analyses of packaging, you'll use something with a very high NA. If you want to look through larger objects, then you want something with a low NA, maybe a 0.1 or 0.2 NA objective. So the key there is actually the design of the system, where we project the depth of field into the y-axis of the detector, and then also matching that with taking advantage of that with the low NA of the objective and looking through packaging and other larger media and high NA for microfine structure. That's a good question.
Yeah, absolutely. Next question here is, can small differences in polymorphs be reliably differentiated?
So that's another great one. So how good can you do in picking up polymorphic changes? As it turns out, the alpha and the Centera and essentially the Lumos as well, everything is on the wavelength axis is accurate to about 0.01 wave numbers. And what does that mean? That means you're not going to collect the data at 0.01. But what it means is that even very, very small changes in crystallinity or polymorphism will shift the band a little bit. And if you look at the Raman, for example, we're at least an order of magnitude better than anyone else in the market. And that has advantage for looking at these small changes in crystallinity and polymorphism, because even very small changes will be picked up because the wavelength axis is so good on our systems.
Fantastic. And next up here is, can recessed objects be analyzed?
So yeah, the recessed objects, sometimes they can be really hard to get to. So we actually designed the ATR crystal on that. Sometimes we call it a pogo stick, so that you can get into those tight areas. Now, how small can you go? The crystal face is about 100 microns in diameter, and you're dealing with an anvil design where it goes to a few times that at the top. You can actually analyze much smaller areas because the aperture gets, or the focal plane array, whichever one you're using, those detector images get projected to the bottom of the crystal face so that you can actually analyze much smaller areas. But as long as your access point is, a few millimeters in size, you can get in there to do a very careful analysis.
All right. And what is the largest object that can be analyzed?
Well, you can look at a textbook, so it's something a couple inches in thickness, and we've actually sold many microscopes where people take paintings literally and put them against the Centera or against the for Raman analysis or against the Hyperion infrared microscope we offer for doing the infrared microanalysis. And for the Raman, we actually offer what's called a Z stage, where we've got customers that are looking at aircraft wings, looking at, because the microscope can be mounted on a gantry. You can look at large statues and paintings and such. So we've actually designed both platforms to be able to look at very large objects, almost any size, really.
And next up here is, can Raman spectroscopy be used for identifying metals?
You could look at metal oxides or metal nitrides or metal carbides, but raw metals themselves just don't have a covalent bond, so to speak. So you pretty much need to move to something like XRF or some other technique. So no, you cannot analyze bare metals with either IR or Raman.
All right, looks like we have one more question here, unless I get a question snuck in here before this one gets answered. But can the polymer density be determined?
That's another really good one. So the density can be determined if it's something that's been known and well characterized, like polyethylene. You can look at the density very nicely, and that's been shown in the literature. If you want to do something that's unknown, you'll have to develop a model, a calibration set of samples with known densities, and then you just you put those into our chemometric models. We have very extensive selection or toolbox of chemometric methods at your disposal, and you can actually do the analysis very nicely and being able to look at density differences. And the key is, if it's a new system that hasn't been done by anybody yet, you actually will develop the model yourself. But it's no different than if you were setting up a quality control, trying to look at how much of the some solute you have in a solvent or whatever. You always develop a calibration set for those chemometric analyses.
Awesome. And I actually do have another question that snuck in here. What kind of sensitivity can I expect for measuring alkanes or amorphous carbon? Can we see monolayers or a few layers on a surface?
So it depends on whether you're doing that by IR or by Raman. So if you're looking at hydrocarbons on surfaces, you can do monolayers and even submonolayers, and you can do them macroscopically or microscopically with the Hyperion microscope. We have a patented grazing angle objective for doing monolayer detection. And if you're interested, just submit your information, your question, or through the chat, so Lauren will flag it, and I can send you the manuscript we published showing that detection. If you want to actually look at something that doesn't have a good signature in the IR, maybe nanotubes or something like that, then you would do those by Raman. And you're not going to necessarily get really good sensitivity unless you have some surface enhanced interaction, which is certainly very common. And we can talk about that further as well. I actually hold a patent, actually 2 patents in the area of surface enhanced Raman spectroscopy. So we can talk about your needs there and probably come up with some good solutions for you.
Fantastic. Well, I think that brings us to the end of the Q&A session and the end of our webinar. Tom, a big thank you to you for presenting today. Everyone who has registered for today's event is going to get a link to the recording once it's available. And that is it from us. Everyone have a great rest of your day, a great rest of your week, and we look forward to helping you expand the boundaries of your analysis. Take care,
Thank you, Lauren.
everybody. Thanks, Tom.